Okay, so in this video, what we're going to do is we're going to look at how to calculate the pooled and unpooled two sample t-tests from raw data. Now, it's much easier to calculate in Excel when we have the raw data than it is to calculate it from the summary statistics because we don't have to deal with the formulas. Everything is built in when we use the test functions in Excel. And so I'm going to show you two different ways to calculate. There's a built-in t-test formula that we can use, and then I'll also show you the data analysis toolpath. Okay, so anyway, the pooled case. So remember that, first of all, both of these cases are assuming that the data is independent. One easy way to tell that is if the sample sizes are different, as it is in this case. Equal sample sizes does not guarantee that it's paired. You want to look at how the data was collected. If you have a particular problem that explains it to you, if the problem doesn't say anything about them being matched or paired, you can assume that they're independent. But if they are the same sample size, you do have to be a bit more careful in determining whether they're independent or dependent, because if you do a test that assumes they're independent, when they're meant to be paired, your answer will be wrong. All right, so these are clearly different sample sizes, and so therefore they are independent, and then we have to decide, should they be pooled or unpooled? Now, the differences here are that pooled assumes the variances are equal. Too many S's. Sometimes this is called homoscedastic. That just means the same variance. And unpooled assumes the variances may not be equal. So it does not assume anything about the variances. This is called heteroscedastic. Now, in an advanced statistics class, you would, not an introductory like freshman level class, but there are tests for testing variances to see whether they are equal enough or whether they're unequal, and they have to be treated as unequal. In our particular case, if you don't know that information, it's generally better to assume that they're potentially not the same and do the unpooled case. But it was once very common to do the pooled case simply because the math is a little easier when you have to do the calculations by hand. You don't have to worry quite so much about how to calculate the crazy degrees of freedom and things like that. The unpooled case can be quite complicated if you have to go through the formulas. But in our case, these are going to be equally easy or difficult to calculate because we have the raw data, and Excel is going to do all the hard work for us. So basically, all we really need to do in this case is go directly to the t-test function. Our first array is going to be the male salaries. The second array is going to be our list of female salaries. The tails, now the tails are going to be determined by what we are trying to test. So if we are trying to test that the two means are equal, and we just want to see if they're different, not who is doing better than who, then we would pick a two-tailed test. And that's what I'm going to do just as an illustration, not making any assumptions about the data. If you wanted to assert, or you wanted to test the claim that men were paid more than in this data set, then you would choose a one-tailed test. Or you could do the other way. You could say men are not paid more, and then you would also want to do a one-tailed test. So if the women were paid more. Wouldn't that be nice? One-tailed distribution. So I picked two-tailed distribution because I just want to see if they're unequal. And then is it paired or not paired? It is not paired. And then if I want it to be pooled, I'm assuming equal variances, so that is type 2. So this is my test statistic. The one-tailed test, remember, this is the two-tailed test. The one-tailed test would have half of this value. And just as a I will just change this from a one-tailed to a two-tailed. And you can see it's just half. So either way, this is not greater than 0.05. And so what we would have to say here is that we would fail to reject the null. This is not enough information to tell if the means are different. Now, if these were equal sample sizes and they were paired data, this might be enough. That's comparing apples to apples. And here we're kind of comparing like all fruits to all vegetables. So it's a little harder to tease out the differences if we're just lumping everybody together, because there's a great deal of variability in both men's and women's salaries. And so unless you can narrow down that variability to like industry by industry or something, then this is why you can't choose paired when it's independent or vice versa. Okay, so that's the pooled case. Now, what we would expect from the unpooled case is that they would be very similar, but not necessarily identical. In the unpooled case, again, we're assuming the variances are not equal. And so I'm actually just going to type this out, and then I'm just going to change some things. So the two-tailed test, it's the same data that we're using in both of these cases. What's going to change is the type. The unequal variance is type 3. And again, you can see the percentage is a little bit higher. And I'm just going to compare this to the one-tailed test, type 3. Yes, I had too many parentheses, sorry. And again, it's half of what the higher value is. Two-tailed tests are just one tail times 2 because they're symmetric. So again, they're similar. Pooled and unpooled are very similar, which is why people didn't worry about the difference so much when doing the math by hand was more difficult. But it is a little bit higher if you don't assume that the variances are equal. All right, so that's the built-in formulas. Let's now look at the data analysis tool pack and see what that output looks like. Again, at the very bottom of our menu, we have, again, the same options: paired, to sample equal variances, to sample unequal variances. The pooled is the equal variances, and variable 1 range is here, and variable 2 range is here. And we did check the labels. We're hypothesizing the difference is 0. Again, we could assume that, like, if men are being paid more, we could put in, let's say, $5,000 each or something like that as a hypothesized difference, but we're just going to test to see if they're equal or not. And then the output range, I'm going to put that right there. And then once everything is in, we hit OK. And we get a little bit more information, which is useful. So it's going to tell us what tests we conducted. It's actually given us a bunch of this test statistics instead of just giving us the p-value, which is this one down here. It's the same as this one up here. It's also giving us the means of both groups, the variances of both groups, the observations in both groups. It's calculating the pooled variance for us, which is actually going to be very useful if we want to then calculate, for instance, a, shall we say, a confidence interval later on. And then, but it gives us all of this information. It also tells us what the degrees of freedom was for this particular problem. And notice that it's 21, 12 plus 9 minus 2. And we can do the same thing for the unpooled case by choosing the unequal variances option. And again, males, females, labels, no mean difference, output range. I'm going to put it right here. And again, we get all these summary statistics. These look exactly the same as we had over here. The degrees of freedom is 16. That's part of the reason why our p-value is a little bit higher. The degrees of freedom is smaller. Our test statistic is a little bit different. But we have our p-value here as well. So again, it gives us the summary calculation for us because we have the data. We can get a little bit more out of it than just the p-value. But again, if you're not using the data analysis tool pack, the p-value is what you need in order to make your conclusion. And so the t.test function is perfectly adequate if you don't need this additional summary information. Notice that one of the things that's missing is there's no pooled variance calculated here because we're not assuming that there is a common variance. All right.